General relativity, step by step. We've been looking at the Einstein field equations, the linearized Einstein field equations, hoping to find solutions that correspond to gravitational waves. And I've gradually been simplifying the solution that we've got, and I'm down to the point where I've got this nice wave-like solution here with a constant second order tensor here, A dash, multiplied by an oscillatory term here. And what I was hoping to do last time, but didn't quite finish, was to use my gauge freedom in terms of theta to perform this manipulation here on the elements of A dash, hoping to simplify them so I can get the first row and the first column of my A dash matrix equal to 0. And I'm going to show you how that works today. We came up with this rather formidable looking set of equations here, but I'm going to show you today that they're not as bad as they might appear. What I want to do is to go back to considering my K matrix, K4 vector, I'm sorry, and that's going to be equal to KT, KX, KY, and KZ. We're writing it with the downstairs index there. It's upstairs here, so I'm going to have to raise that index in a minute. But we know that K alpha, oops, I've written an underline there. Just a minute, let me get rid of this. Equals 0. So that tells me that KT squared plus KX squared plus KY squared plus KZ squared equals 0. Oh, sorry, that's a minus, isn't it? Because the flat space metric we're using, minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And I'm effectively looking at K alpha, K beta, eta alpha beta. Summed over alpha and beta, of course. What I'm going to do now is choose an orientation in which these guys here are 0. So I'm basically going to consider a wave propagating in the Z direction. So I want to make these components here equal to 0, which I can always do by rotating my coordinate system. Rotate my coords. Just with the regular orthogonal matrix. Orthogonal matrix. So I can always do that, and that's no problem. That just involves rotating my coordinate system. So if I write K alpha as equal to, I'll just write it out in a nice form, let's call it A, 0, 0, B. We know that A equals plus or minus B, and it's conventional to write, when you write it with the downstairs index, you normally write it minus omega, 0, 0, omega. And of course that means that when you write it with the upstairs index, because we're multiplying by this matrix here, we get a plus omega, 0, 0, omega. Now that's quite nice. That should allow us to simplify our relations. This of course is the frequency here, and this guy here is the wave number. Right, now what have we got? Let's just have a look at this. Okay, well I'm just going to remind myself what my K is. Put it there. I'll write it as far to the left as I can. So we've got K upstairs alpha equals omega 0, 0, omega. I'm not sure why it does that. That's a 0. So I'm just going to substitute in 1 by 1. So that tells me that 0 equals A, T, Z. Remember the point of all of this. We are given this A matrix here, and we want to, this is given by the physics of the situation, and what we want to do is to find a gauge transformation, theta, a theta transformation, that allows us to simplify this matrix. And the simplification I'm seeking at this stage is to make the first row, this interface is going to drive me nuts, this row here and this column here, make them equal to 0. So what do my equations look like? Well, this one here, KT is equal to minus omega times BZ equals, see this, oh no, that term's not equal to 0, that's minus omega BT. minus omega bt equals 0. I was going to say that's a little bit harder than I was expecting to see, because what normally happens is you normally start up here. You normally start here. I should have done this. A tx. Let's just show you what that component is. That's this component here, minus omega for this term here, bx. You see this term drops out now. That's a 0, equals 0. So that's nice and simple. We can find bx. It's just a tx over omega. This one tells us that a ty minus omega by, that term there, this term drops out, equals 0. So that means we can find by. And we can also find bz. Oh no, we can't find bz because we don't know what. For some reason I've done it bottom up. Never mind. Let's go here. That says that 0 equals, let me just copy it out, a tt minus omega bt minus omega again bt, because we've got two identical terms, minus k pi b pi, summed over pi there. Okay, well that gives us 4 equations and 4 unknowns. We've got our 4 equations, 1, 2, 3, 4. Everything's linear. Yeah. And we can just write down what bx is from this equation here. We know what by is from that equation there. And then we've got 2 simultaneous equations to solve here simultaneously for bz and bt. It's going to be a complicated solution, of course, but there it is. That is B in terms of the A matrix here, or the A tensor here. So we can now work with a much simplified system. We can now assert that that's a K. H bar mu nu in the transverse traceless gauge equals A dash mu nu e to the I k alpha. Oops, I wrote a K again. Just a minute, let's delete that. This interface is playing around. This is not a good advert for OneNote. K alpha. Where A dash mu nu is now equal to the following object. We've got t, x, y and z as columns. We've got t, x, y and z as rows. And we can correctly fill in zeros here by dint of 2 things. By dint of firstly choosing an orientation for my coordinate system that gives me these expressions here in its most general form for my wave vector k, and also by transforming with a further gauge transformation theta. Right, I'm going to stop there, and we've still got quite a large complicated mess of 9 numbers here to think about, but we'll sort those out. Actually we haven't. We've only got 6 degrees of freedom left, because this is known to be symmetric. 6 degrees of freedom left. Stop there. Stop.